Okay, I guess let's start. So last week we talked about arrays, and this week we are talking about a slightly related topic, which is random numbers. Why this is related, you'll see during during the lesson. So first of all, you might have this well-justified question: why do we even need random numbers or this randomness? I guess goal number one would be actually entertainment. Let's say various games and so on that are based on luck. So gambling and video games, etc. Or if you've ever played something from Diablo series of games, then you might be aware of this idea that even let's say this dungeon level itself might be generated randomly each time you play this, so it isn't exactly the same. And in order to implement this, again, you need some sort of random numbers. Otherwise, you wouldn't have it. I mean, entertainment is let's say, I guess one of the more important elements of it. Another one is cryptography. This is an entire topic in itself, but for example, let's say you want to encrypt some large contents, the entire contents of the hard drive or something like this. And there is some sort of key that exists that would then solve the entire hard drive. The key is actually short compared to what size of the hard drive is. The key is maybe, I don't know, 20 characters or something like this, or maybe 100 or whatever. But still, it's fairly small. But this key is then going to be used as a seed value for a random number generator. And then the entire contents of the hard drive are also encrypted with using those random numbers. So they turn this information that was there pretty much unreadable unless you are able to generate exactly the same key again. Then there are other items. So, for example, in the case of networks, so everything is on the internet these days. But there can be issues, for example, that this network becomes congested. That there are, there is this thing called DDoS, distributed denial of service attack, which is basically what is a malicious approach. But I mean, the idea is to create congestion at some sort of server so that nobody is able to access it. So therefore, they get this denial of service message because the server is overloaded. Yeah, this can also happen without, let's say, malicious actors, but just simply, there is a lot of traffic, and at some point, this traffic starts to collide, which means that all the packets that were sent are going to be discarded, and then let's say the network protocol has this built-in system that, in the case of congestion, they won't try to immediately send the packet again, because this would make the congestion even worse. It would increase the problem. So instead, they need to wait some amount of time. But if everybody waits the exact same amount of time, then you just have like there is congestion, then there is silence here, and then there is a new wave of congestion. So this wouldn't solve the problem either. And therefore, you have this random delay, which then means that somebody sends the packet again almost immediately, but somebody waits. And then the hope is that this is going to then reduce the load on the network and solve this congestion issue that somebody's finished downloading their torrent. And then this isn't causing problems anymore. Anyway, and the topmost one is testing. Testing is important at hardware level or low level. But when you design something, you want to be certain that it's during the production it's actually made exactly as you wanted it to be. And then how do you check it? In the case of something as complex as a CPU, which has a lot of these. A lot of operations and so on. And you can construct a test which then will check everything. It will take years to complete. Or you can have this this test that doesn't cover everything. It generates these random values, performed operations, and checks whether the result is okay, and this will be considered good enough. You know, if there are issues, for example, in the case of CPUs, or for example, in the case of let's say GPUs. You know, if you look at NVIDIA or AMD or actually Intel as well, I guess these days, yes. Well, let's focus on NVIDIA maybe. Yeah, you may have a chip which is exactly the same, but out of this chip, different products on it. That you have, let's say, 5080, and you have also 5070, which use exactly the same chip. And the difference is, you know, that you have this chip. You have all these various logic blocks connected by some sort of bus, and then you have large amounts of cache at both sides, etc. And during testing, it turns out that this is not working. And then what do? One of the options would be to discard this entire chip. Or the other option is that it's not going to be 5080, but it can be 5070. So yeah, this is the one, and so on. So but again, in order to test this and be certain that these work correctly, usually these chips have something called BIST, or built-in self-test. And this actually uses random numbers, and generates these various values, then performs the arithmetic logic operations. And if they turn out to be correct, then we can say that okay, fine, this section of the chip works as it should. Or if there are some issues, then it will be entirely turned off, even though possibly 90% of this part here also works correctly. But a small percentage doesn't, and this can cause massive issues if you let it be. Additionally, there might be another issue that this chip is not, or this portion of the chip is not able to work at full speed. But if you reduce the speed of let's say the clock rate of the chip by, I don't know, 20% or something like this, then this will also perform correctly. It's just there are more delays in the implementation of this chip logic than was planned. But then again, you might be able to reuse it for a lower tier product or something like this. So that's why the top line. Currently the top line is 5090, but it has its own chip. It used to be the case that the 90 and 80 series had exactly the same chip. But yeah, this is no longer the case because capitalism and whatever. But the 5080 and 5070, I think, use the same chip, and then if you go lower, then you have an next tier chip which is immediately designed to be smaller. Anyway, so this is for testing, hardware testing, but there also exists software testing. Like I said, we have been talking about those subroutines or functions for a couple of lessons now. And again, we write the code, and it would be nice to figure out whether it works correctly or not. And in fact, random numbers could be used. So we can write some sort of test for our function. And this test is going to give it, all kinds of inputs. And then we need to see that it performs correctly. It doesn't cause any exceptions or errors, or it doesn't crash if we give it this data. So it needs to have those various built-in controls. And some of this stuff using random numbers is going to be values that you couldn't even think of. And then this is why for testing this can be useful. Then you can again build this test yourself. Think about all the possible corner cases, but this takes a lot of time and energy, and you might skip something. Okay, then no, this hasn't been. So this is an example from video games. Is the name of the slide, which I have forgotten to translate. So. But anyway, so let's say we have some sort of game, and in various video games, do you play video games? Okay, at least some people not. Yes, nice. They might have even before you perform some action, especially in the case of turn-based games, you might be given a probability. That the probability of, let's say, hitting the targets is 90%. So do you want to hit this target that the probability is 90%, or another target where the probability is, let's say, 60%? You need to make your choices. But I mean, how is this implemented? Let's say you can generate a random number from 1 to 100, and if the number is less than 90, then the target will be hit. But if it's greater than 90, then you are still going to miss. Even though 90%, it looks like it's almost a certain thing that you are going to hit the target. And why do I bring up this example? There was a game, I guess, a decade ago already. And I've forgotten its name. This is usually the case. Anyway. So the first version of the game had, again, this turn-based combat, but you were able to save in the middle of combat. And this is called save scumming, that you don't play the game, but you're trying to cheat. That you save, you perform the action, see if it succeeds or not, and then you reload and perform it again. And the first implementation of this game had actually this random number generator that didn't change when you reloaded the game. So we were able to see, basically guess what the generated random number was. So you save, you perform a shot that is 90%, has 90% probability. If this succeeds, then you reload and you try another shot which has, let's say, 80% probability. And so on, until you can make a shot that has, like, I don't know, 30% probability. But this random number that was generated was very small. And so you don't want to waste it on something that has 90% probability. So, but again, this was not a reloads. But then you could have almost a perfect, let's say, attack on something, because you didn't lose any soldiers and so on. But yeah, this was patched. So if you try to play this now, then in case you reload, this generated random number generator is going to be reset, and you are going to get a different random number, which means that this strategy no longer works. Then we can talk about video games, for example, let's say MMOs. Massive multiplayer online games. Usually there are some role-playing games or whatever. You can gather a loot, and let's say you have some sort of raid boss, and you have a legendary mace that the boss might drop if you kill him. but the probability of this is very low. Let's say, I don't know, 1%. 1% is impossibly high for MMOs. This is usually 0.001%. Because there are very many players and so on. But okay, let's say we have we have something which has much higher probability. But I mean, still, even if it's 1%, you know, if we use exactly the same strategy, we generate a random number from 1 to 100, and if that number is less or equal to 1, then the maze drops. Otherwise, you know, you get some random garbage. If you look at this, then it's really demoralizing, isn't it? Because I mean, if that's the case, then you have 1% probability, which actually is even high in the case of MMOs. Then this means that you can keep playing this every week, and you play for a couple of years, and you still never get this. So that's why, you know, usually these MMOs have implemented some sort of fragment system that, you know, you kill the boss, but you get a fragment of the maze. And once you have enough of these, then you can forge this maze yourself using, you know, additional materials which are expensive, or maybe which you can get from the cash shop. But I mean, what could be done if we don't want to use this approach? Is that actually, you know, we can keep the statistics about the player. You know, we take into account that, you know, he or she has already played this raid, whatever, and killed the boss a number of times. And therefore, instead of generating a random number from 1 to 100, you are going to generate this from 1 to 100 minus number of kills multiplied by some sort of coefficient. And then this might mean that at some point, this value is going to become, you know, greater or equal to 100, which means that it's 100% certainty that you're going to get this thing. But you know, if you're unlucky, then after you do it like 50 times, you're still going to get the base. And then there's an expansion pack which makes it obsolete. But anyway. But now, how are these random? So we have talked about these random numbers that, you know, they have various uses. So let's say in the case of cryptography, let's say in the case of testing or entertainment. But I mean, how do we get these random numbers? And now this is, let's say, the main topic today. So it's possible to use noise, but this is kind of complicated. And what may happen is that the distribution has poor the probability distribution has poor quality. Because usually, in the case of these random numbers, you want it to have a certain probability. You know, there is this normal distribution which looks something like this. Then you have this average value. Okay, not exactly like this, but something like this. You have this average value, and here you have a large grouping around this average value. And let's say this distance here is called 3 sigma, for example. And sigma is dispersion of this probability. So 3 sigma covers like, I don't know, 97 or whatever % of these of those cases.
I mean, if it goes from here to here, right? And then there are some extreme cases which are not covered. I mean, this might be even higher. I'm not really that certain. It has been a couple of decades when I last took probability theory. But let's say this is one of the probabilities. Probability distributions. There is another, which is that we have some sort of minimum value, we have some sort of maximum value, and actually the distribution is like this. But the probability of hitting any value within this range from min to max is equal. And a lot of these random number generators try to create this sort of probability distribution. But yeah, if you use noise or heat or whatever, then the likelihood of it might very well be that it is the distribution is something like this. That's it's symmetrical, let's say, that it starts and so on, and then this is using this is complicated. So therefore, noise is not a good approach, even though still I think noise can be used for initializing the random number generator, which is then actually some sort of deterministic method. Which is, yes, the second possibility, that we use a deterministic method which generates a random number as some sort of function of previous number. And this is easy to implement. We'll look into how this can be done. But now these random numbers are no longer random. They are called pseudo-random numbers. So, all these terms, random number generator, whatever, usually doesn't really talk about random numbers, but they are pseudo-random numbers. Because the sequence is going to always be the same. But on the other hand, the probability distribution has excellent quality. It has, for example, this what is this? Equal, or the probability of any value is equal to any other value. So let's look at some methods how these deterministic methods, these deterministic algorithms can generate those numbers. And first one is called linear congregational generator, which is the following idea, that we have an old random number x n minus 1, and xn is going to be a multiplied by the previous number plus c, and then we perform the mod operation, which is basically division with remainder, and this is how we get the new number. So this n is usually a power of 2, and this may very well be the size of I don't know, 1 byte or 2 bytes or 4 bytes, and then it generates a random number within this range from 0 to m minus 1. And so the main issue here is that those variables a and c must be really chosen well. M is actually not 3, but it should be 8 here. But anyway, yeah. So let's say a is 5, c is 3, m is 8 or 2 to the power of 3, and x0 is 0. What's going to happen? So we have 0 multiplied by 5 plus 3, and then we divide it by 8 and get the remainder. So it's going to be 3. next we're going to multiply 3 by 5. We'll get 15. We add 3, we get 18. And then we divide by 8 and get the remainder. The remainder is going to be 2. And so on and so on. So actually, we get all those numbers, the sequence. And then once we hit 0 again, this period is going to repeat, and we're going to get another exactly the same sequence. So in the case of, let's say, 3 bits, right? This is the number of bits. It's maybe not that impressive, but I mean the same pattern repeats if you go larger as well. If you have 16 bits, so 65,000, or 32 bits, so 4 billion. Exactly the same idea repeats. But again, it depends on those values A and C. So in the case of 3 bits, this was pretty easy. But we can mess up here as well. That, for example, let's say A is 7, C is 3, and M is 8. And the first value is 0. Then the issue is going to be we are going to multiply 0 by 7, and then we get 3. Add 3 and then divide by 8. We get the remainder of 3. And next time we're going to multiply this by 7. We get 21. We add 3. We get 24. We divide it by 8, and we get the remainder is going to be 0. So actually, the period is going to be just 2 numbers, 3 and 0, and this is it. So this is not a good generator. And again, this is not translated. So for example, if A is 11, C is 3, M is 3, then we get 3, 4, 7, 0, and again the period repeats. So let's say this is an average generator. So many stuff was untranslated. What a poor showing. The quality of this linear congregational generator depends heavily on the choice of constants. But since this method is simple and is very widely used, and actually in C language, this rand function itself also uses this method. And depending on the platform, the constants may vary actually quite a lot. This used to be, for example, the case. Then when you install, let's say this on your own computer, some sort of environment for editing, and then you also need the compiler, and usually with the compiler, you need some sort of environment that, Microsoft has a compiler as well, but I'm not sure if they offer it free. At least, I mean, they didn't for a while, and nowadays they have sort of delegated it to the open source community to provide it. But anyway, one of the options was this minimal GNU for Windows, and this used to be 32 bits. Even though all the computers have been 64 bits for a couple of decades now, but 10 years ago, at least, it was still 32-bit that you could download. And this meant that the random number generator generated numbers in the range from 0 to 32,000. And, so running out of those numbers happened incredibly quickly, which is one of the reasons why I don't like this thing. But anyway, nowadays it's 32 bits, so it generates values from 0 to 2 billion, not 4 billion, but 2 billion. So only the positive values. And additionally, internally, actually, it uses 64-bit values. but only a portion of the generated value is used somewhere from the middle. So we have 64 bits, but so we take like bits, I don't know, 8 to 40 for our random number. The advantage of this method is that it requires very little additional memory. We just need to store the last value. And this function is shared within an application. So anybody who calls this random function is going to use the same value. So what this means? I mean, you're not going to pass the previous random number to the generator. But instead, this is one of the cases where something can be a global variable. Let's look at an example. So, and today, so this is this one, LCG. So this is, hopefully a very simple example. So we have main program. Here we set x to 0, and we use this to seed our random number generator. And then we have some additional values. We have I, which is an iterator, and y, which is going to be the next generated random number. And then we have a loop which continues until x becomes equal with y. And within this loop, we are going to get our next random number, or pseudo-random number to be more precise. We're going to print this out and say what is the index of it. And then we are going to increment this index. Now, so the seed function is basically, we are going to set our global variable. So this rand LCG is going to become the value of seed, and we are going to print out that what was the initial seed. And therefore, yes, this is what we have here. We have a global variable about which I said, a couple of weeks ago, and I have already complained to some of you if you have turned in this homework, which is using global variables, that this is very bad practice. But in this case, everybody absolutely accepts this, that the seed value is going to be a global variable. Because otherwise, every time we call this random number generator, we would have to pass it the previous value, and this is not good practice. So instead, it doesn't take any arguments, but it has one global variable which it updates each time. And again, this the next value is going to be previous value multiplied by a, and then you add c, and then you divide it by m and take the remainder. And these are the constants. So a is, for example, 29, c is 15, and m is 32. So we can compile this and run it. And let's say these are the numbers that we get. So we get 15. Which was the value of c, right? And then we get all these other ones. So 2, 9, 20, etc., etc., until we get 0 again. This happens when we get the 30-second value. So in fact, this uses this entire space, equally. Every value is represented, and this is a good generator. So if we play around and we start changing these values, then this might no longer be the case. Let's set it to 25, for example. Then Actually, with 25 it also works. Okay, let's set it to 24. Okay, and now we have an issue where, in fact, we always get the same number. So the next value is previous value multiplied by 24 adds 15, and then subtract 32. So this is, this set of constants has an issue. But yeah, if it's like this, then, and there is a whole science behind this, then how can you find out these constants that work best for you? Okay, so this is the LCG algorithm, so to speak, for generating random numbers. And like I said, C1 actually uses the same thing. So next there is a simplification of this algorithm, which says that we don't actually need to add anything. That xn is going to be this a multiplied by previous value, and then you divide by m and take the remainder. This is going to cause some problems. So first of all, now you are not going to get the entire range because you have to exclude 0. If you multiply something with 0, you're going to get 0 again. So then you get an infinite loop, right? Yeah, this is less stable. But I mean, you have one less operation, so to speak. So let's say this is the main advantage of this. So let's say A is 5, M is 7, x0 is 1. Then you get values. So we multiply 1 by 5, we get 5. We multiply it by 5 again, we get 20. Now 20. No, we get 25. If we divide this by 7, then 21 had this value, so we get 4. We multiply 4 by 5, we get 20. So 14 is divisible by 7, so 6 is the remainder, and so on and so on. So this is fairly good generator. But again, if we take, let's say, 4 and 7. Then we get, and the initial value is 1, then we get just three numbers, 4, 2, and 1. And then the period repeats. So we don't get 3, we don't get 5, we don't get 6. So yeah, this is poor or average generator. So let's look at this example as well. It's in the files called mcg.c. So it's pretty much the same. So the generator has one less operation, so to speak, but the rest of it is exactly the same. So the m in this case is 31, and the a is again 29. And this is going to generate actually only 10 numbers for us, and then it's going to repeat. And what else? If we initialize it instead of 1 to 3, for example, actually, let's see. I have another console here. This was MCG. So these were the numbers that it currently generated. But let's try a different value, and then we get this set of numbers. So it's different, and actually none of them repeat. If they would, we would enter the previous sequence. And actually, there exists a third one as well. So I need another terminal here, which is so this was the second set. This was the first set. This is the second set, and now if I set it to 5. Compile and run it, then we are going to get this last set. So actually, these 3 sequences cover the entire range, but now it depends on the yeah. Now it depends on the initial value, depending which sequence you are going to get. But yeah, this is all the missing value. So these 3 ranges, or these three sequences cover the entire range. So like I said, this is more complicated, but there is one less operation. Therefore, in some cases, this might be preferred. But when we talk about computational complexity, then multiplying and finding a remainder, which is not the power of 2, are considered to be expensive operations. So the next method requires much less hardware, and this is called linear feedback shift register. So here we don't have any of those complicated operations. No multiplication, no addition, and so on. But instead, the idea is that we have a register of bits. Let me put this. And we are able to perform a shift operation. So let's say we have 5 here. So this would be 101. So we are able to shift this, and then additionally, you are going to have, let's say, a logic gate. That's what they call it. We have a logic gate, which takes 2 inputs, has 1 output, and this is then sent in from the side. And the logic gate can be XOR or usually it's XNOR. So the idea behind it, that if we look at it mathematically, then the length of the shift register determines the range, and this operation that we shift all the bits left, we would get, for example, then 1, 0, 1, and the result of this operation is going to be shifted in from the right. And in the case of XNOR, if these 2 are different, then let's see. In the case of XOR, they're different. We get 1, we get 0. So you get 0 here. So from 5 we got a 2, and so on. So so yeah, basically there are mathematical operations being performed here. But since it happens as for multiplication, you will need a lot of gates, and again for division, etc. So you would need an entire arithmetic logic unit. But in this case, you don't need any of this. And this overflow bit is then reused for calculating the lowest bit. And so the new random number is old number shifted left plus XNOR of 2 or 4 bits. And again, there is a whole science behind this, that how those specific bits have been determined that need to be used. So LFSR has one forbidden combination where the next value is going to be exactly the same as the previous value, and usually this is the case where all bits are 1. Let's look at the example as well. So let's say m is 3, and then 2 to the power of m is going to be 8. And bits A and B are 3 and 2. So let's say we start with 0. If we shift it 1 position to the left, so we multiply it by 2, and then we take these two bits. So in this case, they are equal, so the output is going to be 1. And yeah, the exact example that we had. Oh no, we have 101 somewhere. Yeah, we have it here. So what's the case? I mean, we had 101. Which was the value, we shifted it right, and the XNOR is shifted in from the right, so we get the 0 here. If we shift it one more time, then we're going to get 1 0 0, and we shift it one more time, we're going to get all 0. So this period repeats, and if we look at the values themselves, then they are like 1 3 6 5 2 4 and 0. And the forbidden combination is 7, so 7 is not permitted yet. Now, pretty much every value is going to be covered. Let's say this is the beauty of this idea. Plus, it's very easy to implement in hardware. If you ever take a course like Computers 1 or something like this, then this is what you're going to do there, definitely. But I mean, the sequence is going to be less elegant than in the case of LCG. So, for example, we have these values 3 and 6 and 2 and 4, which are, the next value is an exact multiplication of the previous value. And if we look at the LCG example, then that was usually not the case. Or even in the case of MCG, we don't have the case that we have 7 and 14 and 28 or something like this. Usually we don't have this. But I mean, this comes from the fact that this is the implementation is very simple, and you perform this shift operation. So usually, yes, the next value is going to be the previous value multiplied by 2 plus 1 in some cases, or you get an overflow, and then this is going to be cut down. So yeah, this is usually not really used for random number generators in software. But I mentioned this built-in self-test. This is where it's used. Usually you have a linear feedback shift register. This is going to generate a sequence. We know exactly what the sequence is going to be, and then this is fed to the arithmetic logic units. And then you can check the output of the arithmetic logic unit to see if it's correct. If it's not correct, then there is some issue in the hardware, and you can discard this portion of the chip. So yeah, this was the example. And for this, we also have a code example. So this is one of the few cases where we use these bitwise operations. Let's say this m is 5, so we actually use 32 values, or no, 31 values. Then the tap positions for the XNOR operations are going to be 5 and 3. The main function is exactly the same. Seed function is also exactly the same. But I mean, this calculation here looks significantly more complicated in software than it does in hardware. In hardware, you don't really need almost anything. You need this shift register, and you need a single XNOR, or in some cases you might have 4 of them. No, 3 if you need multiple inputs. But generally, it's very simple. But in software, this is going to be complicated. So we can perform this shift operation. That's fine. So x is going to be the current value shifted left by 1 position. So this is pretty much the same as multiplying it by 2. Then we apply the mask. For mask, we are going to check whether the specific bit at this position is 1 or 0. So we are going to shift it left 5 positions and 3 positions, single 1. So this is a 1 bit. And then we're going to see whether, using a bitwise AND operation, we get a value that is greater than 0. If it's greater than 0, then, those bits were set. Then C is going to be whether both of those bits were set. And now, depending on XOR or XNOR, we perform different operations. So in the case of XOR, it's exactly if one of the inputs is 1 and XNOR is inversion, so it's 1 if both the inputs are the same. So if both are 1s or both are 0s, then this C is going to be 1. And we have mask as well. So in this case, we set all the bits to 1, and we shift it to right by the length of this linear feedback shift register. And then again, we perform this operation. So we take this new value, we OR it with C. So this is pretty much, let's say, logical addition. And then we apply the mask, which would then cut off any overflow bits. And so basically we get x plus c, and then remainder of the operation when we divide it by 2 to the power of 5 in this case. But these are all, like I said, bitwise operations, and therefore they run significantly more quickly than actual multiplication and division and so on. And this is pretty much it. So this is quite complicated. I guess you would agree. But I mean, in hardware, it's almost trivial, so to speak. So the other operation, looks trivial in software, but let's say the hardware implementation of it is quite complicated because you need multiplication operation and you need division with remainder operation, and these are usually huge blocks of hardware, depending on what sort of operands you are working with. But yeah, the software side of this looks pretty awful. But let's see. This is going to generate for us these kinds of values. So, like I said, you have 1, 3, 7, 14, 28. So this is pretty much grows all the time. Then you have 25, 18, and then another sequence: 4, 8, and 17. 2, 5, 10, 21. and so on and so on. So 6, 12, 24. So let's say it's less elegant, but again, each value is represented only once, so the probability is equal for all those values. Okay, then if we talk about C itself, then usually nobody wants to implement this random number generator themselves, but instead they want to use already something that exists. And in C, in this std_lib library, you do have a function called rand, which generates one number to from 0 to 2 billion. So this m is 31 here in this case. And so, like I said, depending on the platform, it could be either 15. In this case, you get a value from 0 to 32,000, or it can be 31. Then you get a value from 0 to about 2 billion. Internally, it actually uses the same LCG algorithm that we talked about in the very beginning. So it's this algorithm. And then the downside of it is that it always generates the exact same sequence. Well, that was also the case with our examples. Then we always run it again, we get the exact same sequence. But if we use the random number generator provided by C itself, then it still has the same problem. So they have this uniform distribution, which is the main advantage. And let's see this example as well. This example would be then this run.c. So this is, like I said, completely trivial. We need to include the std_lib library, and we can seed it, but that doesn't really matter. It's also seeded automatically by some kind of default value. But let's say we seed it with 0, and then we run it. But now the issue is the numbers are going to be very huge. So we want to take some sort of subset from it. And for this reason, we are going to divide this again by some kind of range and take the remainder. Then we get values in a specific range. And so in this case, actually, even though the range is only 32, we don't really get 32 numbers, but we get 130 numbers. Because, what happens is, even though we have uniform distribution, after performing this division and taking the remainder, we no longer do it. And therefore, if you look at these numbers, then there are some repetitions here. I think there was, there were like 3 ones in a sequence. So you can say that this is no longer actually uniform distribution. But other than that, the numbers themselves are pretty decent, so to speak. And yeah, this is the, let's say, random numbers in a specific range. So we need a different range. Then we can again take the remainder from division with the size of desired range. And additionally, we can add the start of the range if we don't want to start from 0, but we want to start from somewhere else. Let's say from -10 up to +10. The size of the range would be 21, and the beginning of the range would be -10. There is one thing to pay attention to, which is this round max value. So this is the maximum number that can be generated by the random number generator. And if it's very small, like in the case of 32-bit this Ming environment, then yeah, it's only 32,000. You want to generate numbers from 1 to 100,000, then they're never going to go beyond 32,000. So if we need a larger range, then then we need to do some additional steps. Either we multiply the two random numbers, or we multiply one with a specific value and then we add the other, or something like this. So both changing the range and doing these additional operations are going to negatively affect the quality of probability distribution. It's no longer going to be exactly uniform. But this is the best we can do. I think we need, so this is all for integers. If we need real numbers, then we can do the trick that we divide this by rand max, and then we multiply this by the size of the desired range, which would actually bring us to fixed point real numbers, because I mean that's how they work. That we're going to use them in some different range. So originally it's an integer value, but we perform this division and multiplication, and then we get a fixed point value stored as floating point value, but this is a different matter. So initializing the generator. So since this algorithm is deterministic, we will always get the same sequence. If we run it, again, we're still going to get 132 numbers. This is not going to change, unless even if we use srand, because if we initialize it with the same constant every time, then it doesn't matter. And so one of the tricks that the programmers have been using for a while is that they use clock for generating the random number generator, for initializing the random number generator. So there is this function called time, which counts the number of seconds from 1st January 1970. And I mean, yeah, this is going to change exactly once in a second. So if your program keeps calling, let's say this time function multiple times, and it all happens within the same second, you are going to get the exact same value all the time. So this initialization should be done once, and then after it's we perform the rest of the operation. So in this case here, we can bring in the time library, time.h, and then the seed is going to be, for example, time null, I think. And then we call srand seeds. This compiles. Okay, now we're not going to get the 0 for a very long time. Okay, so this is let's give a different thing here. While I is less than I don't know, 20 or something like this. So we get 20 values, and if we run it again, we get a different set of values. Wait, 1921. Yeah, it's different. However, if we do this now multiple times within the same seconds, then we get the same sequence. 19, 28, 31, and also 19, 28, 31. Now I do it again, and it's a different sequence. We get 9, 9, 7, and so on. But 1 second is long enough that I can press Enter key multiple times within it. So therefore, yeah, like I said, you shouldn't initialize this random number generator more than once within your program. Otherwise, there could be issues. Or you need some sort of delay mechanism. We'll talk about delays as well. So yeah, so this is these are the, let's say, random numbers. It's a bit of background information. I mean, you don't really need to construct your own random number generator, but I hope at least this lesson gave you an overview how they work, or what's the logic behind those random number generators. They're not really random, they're pseudo-random. But I mean, I mentioned arrays. So what we can do is we can fill an array with those pseudo-random numbers. And now let's say the main problem is we don't really know what the exact contents of the array are going to be because they are random. And this brings us to some new problems. That either we want to calculate some sort of statistics about this array, either we want to find, let's say, the minimum value, the maximum value, or something like this, even though we have specified a range for our random number generator. Or we can also search for something. We can look for some specific value. That is this value present or not? And if we're talking about, for example, set operations, then okay, this let's say the search algorithm, if we're looking for a minimum or we're looking for a specific number, this has linear complexity. But if we need to have set operations that we have two arrays and we need to find what the common elements are in both arrays, then this is going to bring us to quadratic complexity, or n squared. Because we need to compare every element in the first array to every element in the second array, and therefore we have this sort of complexity. There are better algorithms, and we are going to talk about them, but not today. So let's say for sequential search, there are these three algorithms here. First one is just for finding x. So the input is some sort of an array M with length n. And the x that we are looking for, we're going to go through the entire array. So we're going to set the index value to 0. We're going to check that the index value is less than n. And if it is, then we can say that x is not present. Otherwise, we need to check whether the current element in the array is equal to x. And if it is, then we can say that, okay, the x was located at this specific position, and then this loop continues. We increment the index value. For minimum and maximum, it's pretty much the same. So if the n is less or equal to 0, then we cannot do anything. There is no minimum, there is no maximum. Otherwise, we are going to perform our initial guess that the minimum is going to be the first element in the array, or its maximum is going to be the first element in the array. And then we go over the entire array and we update our initial presumption, so to speak. That if we find an element which is less than minimum, then we are going to update this and say that the minimum is now this new element. Otherwise, we are going to keep going. And once we reach the end of the array, we have found the minimum. The same is the case with maximum. Just the operation here is different. For this, there is also an example. I think the example is slightly more complicated than it needs to be, but for find, we have a function. We have this array with the length of n, and we have a value that we are looking for, and pretty much this is what we do. We go through the entirety of this array. If we find the value, then we are going to return the correct index. Otherwise, we're going to return -1, because -1 is index that is not permitted. So therefore, it's outside the valid range. For minimum, it's pretty much the same. It's the exception that we check whether the n is less than 1. In this case, we don't have an array and we cannot perform this operation. This is the reason why we need to check for this. And then otherwise, we're going to go over the entire array. You are going to check whether some value is less than the result. And if it is, then we update this, and at the end we are going to return it. Then for find maximum, this is pretty much the same. You are out.
Sorry.
For maximum, this is pretty much the same. We go over the entire range. Initially, we make this guess that it's the first element, but otherwise, then we are going to compare it to each element and update it when necessary. And then for generation, we're going to give it this minimum range, minimum value, maximum value. And so the range is going to be maximum minus minimum plus 1. So like I said, if we want it from -10 to +10, then it's going to be 21, not 20. Even though you might think that it's you get from you subtract from 10 minus 10, you get 20, but the actual range is 21 because you want to include the maximum itself as well. And 0 is a number. If the range is negative, then we're going to set all values to minimum. Otherwise, we are going to take this random number divided by this range, and then add the minimum value. And there are some other things like find width, which uses a different method for figuring out how long a number is. That it has this buffer. It's going to print out the minimum value to buffer and then check what the length of it is. Or it's going to print out the maximum value to buffer and check for its length, and then it's going to return the maximum of those two numbers. This is related to next week's topics, which is going to be text. So let's not go into this much more at the moment. And then we have display, which is going to print out all the elements, and then we have a main program, which mainly talks with the user, asks for the size of the array, for the minimum, for the maximum, then for the search value. And then it's going to say that, okay, the actual minimum and actual maximum are the ones that we find in this array. So let's say the array is 10, and minimum is -10, and maximum is +10, and we're looking for value 5. So the actual minimum and actual maximum were -9 and +9. So actually the range was slightly smaller. And we also found the value of 5, which is nice. If we do this again, let's say it's 20 and it's from -5 to 5, and we're looking for the value of 1, then we have a lot of repetitions. And the actual minimum and actual maximum are indeed -5 and +5. And we also found value of 1, even though the value of 1 actually exists here multiple times, but we are looking at the first value. So these are the examples for this week. Do you have any questions? If not, then let's look at the tasks, and there are 2 tasks as usual. So the first one is a random array, and I am looking for an algorithm. It's another problem. So this was the first task last week as well, that I wanted an algorithm. So pay attention to the wording of these tasks. So we are giving step S and an array with length n. So we need to make an algorithm that takes these 2 integers as inputs, and then it should construct an array M as follows. So if n is negative or 0, then there is nothing to do. If S is negative or 0, then array M should be filled with zeros. But if S is positive, then the first element of the array should be 0. And the next elements of it should be random multiples of S in ascending order. So actually we want the array to contain values in a specific order. But the next point is important. Sorting is not allowed. So you cannot sort this array. So again, how would you do this? And the idea here is, again, the next element should be the previous element plus some random number, for example. You can multiply this random number with step, for example, or you can just generate a random number and see if it's exactly divisible by S. So let's say if S is 5 and n is 10, then the array would be 0, 15 or 25 or whatever, but then 45, 130, so on, so on, so on. So it's in ascending order. So every next value is bigger than the last value. But all of them are exactly divisible by 5. So this is the important bit. And yeah, I want this algorithm. And the portion of generating this random number is unnecessary. So like I already mentioned, these various algorithms, you don't need to reproduce it. But you can just say that you pick a random number, and then specify what the range is, and then what else you are going to do with it. So that, like I said, there are multiple approaches. You can keep generating random numbers until you find one that is larger than the previous, and so on. But this can cause issues that you get a random number that is very large, and then you're not going to find more numbers that are greater than it. So yeah, there are some things to pay attention to, and the other one is a game for a change. So there is a file called dice.c in Teams. Which implements a simple dice game. So there is 20 dice. Both player and computer can roll it up to 3 times, and the last result is what matters. And there are five games total. And there is this method of calculating the points. That if there is a tie, then both parties get 5 points. If the difference is less than 5, then winner gets 10 points and loser gets nothing, and so on. So what matters is the difference. So if the difference is, for example, 15 between the value of the dice roll, then the winner gets 25 points. So this can be catastrophic. And so after five points, we calculate the sum of the after 5 games we calculate the sum of the points, and the one with more points wins. So let's say this is the game, and we can also look at it. So this has slightly more complexity than the others. So there is a lot of interaction with the user, but basically we are just going to ask whether the user wants to roll or not. There are variables for total points and for the latest result of a roll. The points are initialized to 0. And then there are 2 index values, and then we have our dice game. We initialize the random number generator using the time value. We don't really want it to always be the same, because otherwise then it's going to be boring, right? And then we go overall over the number of games. So we have 5 games, and within this loop we offer 3 tries first to the user. And there is a function called roll, which is going to generate a random number. So this would be our die roll. And we are then going to ask the user whether they want to continue or not. And if they don't, then we are going to stop, and this is going to be the result of the user. Then there is a small pause. We use microsleep, which is going to be a quarter of a second, so this is 250,000 microseconds. And then it's computer's turn, but currently the computer is behaving very stupidly. So it's simply going to call roll 3 times, and this is your task to figure out, let's say, some sort of logic for the computer. And after each game, we are going to calculate the points, and then print out let's say the current state of the game, until we reach the end of this, the number of games, and then we're going to say that who won the game. Statistics is pretty much, it's going to just check which was it the computer or the player who won. Points is going to give 5 points if both results are equal, but if there is a difference, then it's going to check for this. And then for user, we have this function called stop user, which simply asks, do you want to roll again, and offers keys yes and no, so Y and N. And if we are going to read in one key press, and if it's new line, if it's N, then we are going to stop. And at the end, we are going to return K. Why do we have this loop here? Okay, if we find a single N within this row of text that there was, then we are going to set K to 1, and then we are going to eat up every character up until the end of the line. So if there is a single N lower or uppercase on the line, then we are going to consider this that the user wanted to stop. itself is basically we call this rand function, and we are going to divide it by 20 and take the remainder, and then we're going to add 1 so that we would have values from 1 to 20 and not from 0 to 19. And this is pretty much it. So currently, I get the value of 2. Yes, I want to roll again. I get 11. Okay, let's say I don't want to roll again. And currently, let's say the computer rolled 5, 17, and 8, but it kept rolling. So it should have stopped here. It should have stopped at 17, and then it would have won. But currently, I won. Second game, yes, I want to roll again. No. And yeah, So currently the game is kind of boring. But even if I'm okay. Okay, yeah. Okay, the computer could have won again, but it didn't because it kept rolling. And even the value of 1 again. I mean, this would have given the computer a lot of points, but it kept rolling, and therefore it got 9. Therefore, it could have gotten 25 points. But it only got 15. So the difference is still large, and I get 19. I don't want to roll again, and yeah, I get 50 points. Computer got 15 points, and therefore player wins. So this is not fun. And then your task is to make it fun. Currently the computer rolls 3 times. And write some sort of function that decides whether the computer should continue rolling or not. And this function then can take into account the following things. What is the result of the computer? What is the result of the player? What is the number of the roll? So if it's second roll and you get 15, do you really want to roll the third time? Maybe not. If it's first roll, then maybe you are willing to risk it. And then the sum of total points for both player and computer. So if the computer is really far behind, then maybe it's permissible to be more desperate in its rolls. And also the number of remaining games. So you don't have to use all of these. You can actually use only 2: computer's result and player's result. But you can take other stuff into account as well. So it's up to you to sort of, 10 years ago this was called AI. Even though it's just a number of if-else statements. But basically, since we have this random number generator, we can generate these random numbers. We can use it for entertainment, and this is the example of it. So you should make this function, and then during defenses explain what your logic behind this function is. And that's pretty much it for today. Any questions, comments? So there are a lot of people online. Is everybody ill or what's going on? The classroom is becoming kind of empty. Okay, but that's it from me today.